So hello everyone again. Welcome to the Developer Growth Summit and of course leveraging async and await in modern Python. A few quick instructions first just before we get underway. We are using Zoom webinar. It's completely normal. You can't see each other, but there are people, as we've just established from chat, all over the world here. So please feel free to interact with each other, make connections, network, all the fun things. Just make sure that it's set to everybody, because it often defaults to hosts and panelists. You'll also notice at the very bottom, there's a Q&A button on the toolbar. This is where you can ask questions during the talk. We will get to them at the end of the talk, unless they're super pressing. But yes, I encourage putting them there because if they're in chat, I may miss them. Yeah, what else? Sorry, there we go. Code of conduct. This is a very safe and inclusive place. We do have a code of conduct to proceed with the session. So keep the chat wonderful and inspiring and excellent, and we'll have no problems. And let's move through. I want to introduce now Michael Kennedy, who is our speaker for this event. Michael is an avid Python and MongoDB enthusiast, an entrepreneur, and the founder of Talk Python Training, along with being a Python software Foundation Fellow. So we are in very safe hands for this talk. So without any more further ado, Michael, please take it away.
Hey everyone, nice to meet you. Great to be here with you. It was cool to see all the locations you're coming from. I'm reaching you from Portland, Oregon, west coast of the US. Let's just jump right into some slides and some ideas. The first question after all of the is this being recorded is, will I be able to get the code? Yes, you will be able to get the code for this presentation. I put the link in the chat. I'm just reusing this webcast I did a little bit ago, so I'm not creating another GitHub repository, but it's very much quite similar, so good enough for that purpose. So in this section, in this webcast, we're going to talk about asynchronous programming, and in particular, asynchronous programming in Python. Now, Python's had a bit of a storied history around threading and async and other oddities like multi-processing and whatnot. But since version 3.5, which I'm trying to think back, 4 or 5 years ago, this has been really enhanced with async IO and the async and await keywords. The async and await keyword programming model it really seems to be taking over, right? We've got C# has had it for a long time, and was it Anders Hallsberg who introduced it? Very nice pattern. JavaScript has it, Python has it. So it's, even if you're not doing Python, what you're going to see here is applicable also to JavaScript, also to .NET. So a little bit of extra bonus there. However, a lot of these programming models have a alternate way of thinking about concurrent programming. So when you think about traditional concurrent programming, you think about work happening at the same time in multiple places. So for example, I might have a multi-core processor and I could create 2 threads and do computation on both of them instead of on one. And that would be stuff actually happening at the same time. But I want you to think a little more broadly about that idea for this session. So if you go to Wikipedia, they'll tell you that asynchrony, as in asynchronous programming, refers to the occurrence of events independent of the main program flow and ways to deal with such events. These may be outside events, such as the arrival of signals, say like a web request coming in, or actions ingested by the program to take place concurrently with your execution without the program blocking or waiting. Nowhere in this do you see you must create multiple threads that run on different cores, or you must create multiple processes that then coordinate in some way, or even scale out across machines in some grid compute thing. It's just stuff happening at the same time without blocking. So keep this more broad definition in mind. So there's 2 core uses for asynchronous programming. One is for speed. I want a single thing I'm doing. I want to try to take better advantage of the hardware that I'm on. If there's this really sort of historical article or approach here about following along with Moore's law. We all know Moore's law is like every 18 months, the number. We used to sort of think as computing power doubled every 18 months. But that's not really what the law said. It said the number of transistors in a processor doubles. And that used to be basically linearly tied to the performance. But notice around 2005 and onward that the Moore's law curve and like sort of processing speed, think single core speed, have diverged since then. And now what we have is computers that are just about as fast as they were 5-10 years ago, but they have way more cores. Okay, so if you want to have your code run as fast as possible on modern processors, it's not enough to just make it run. You have to run taking advantage of all these different cores. All right, so for example, in Python, if I write some code and it's by default single threaded, as is almost every programming language, it is in C++, it is in C# and so on. Unless you take action, it's single threaded. And notice this example here, I've got basically a while true loop, just hammering the system as hard as I can running here. And look at the processing. I could actually show you this over here on, let's reconnect to my Alienware machine here. And now we can go over here and we could say Python, and we just write the code x equals 1 while true, x plus equals 1. And I'm about to hit go, but there's this cool program. This is the reason I'm doing it on Windows, not my Mac, which you're going to see more of, is there's this great program called Process Explorer that lets you really understand per core how the processing is happening on your machine. So you can see there's a few little random background things happening, but not much. But if I hit go, it looks like almost nothing's happening. In fact, this thing is going as hard as it can, but we're only leveraging 6% of the processors. I mean, we've got 8 hyper-threaded cores, and look, we get almost no usage of this computer, right? So if you want to take advantage of all the processors and basically the computer you got, you have to use some other mechanism. All right. By the way, when you're thinking about this, you're always adding complexity when you're doing parallel programming. And you should think about how much benefit will I gain from doing this thing. So for example, if you've got this workload here, and there's maybe 15% of the time this part of your algorithm could be made concurrent, and this other part over here, this other 5% could also, if you could imagine like an unlimited or somehow harnessing every processor in the world and turning it loose on your program, still the best you're going to do is only an 80% increase. So if this happens in 1 second, is it really worth adding tons of complexity to get it in 0.8 seconds? Maybe it is, maybe it's not. It depends how big those green bars are, how much that margin matters, and so on. But just always keep in mind the upper bound for improvement here. So that's interesting. But oftentimes people talk about asynchronous programming not for making an individual thing go faster, but to allow for more of it to happen. So if you're in like a data science world and you want your computation to go faster, this CPU bound story is what you're thinking about, right? You've got 1 million records, you want to do a bunch of computation. It'd be nice to make that happen in 1 minute instead of 10 minutes, right? So then you're in that mode. Over on most of the other places, it's about, I've got some service and I want it to be able to have more users. Or as I add more users, I don't want it to slow down, things like that. Or even in a more focused way, maybe what you need to do is, I want to access a couple of microservices or some external APIs in a database, and I want to be able to have those things happen at the same time, but not in a computational way. Okay, so let's think about this real quick. Imagine we've got an API or website or whatever, and these green bars, request 1, 2, and 3, these represent how long it takes to process one of these requests. Now, if we execute this in a synchronous way, and you think about, well, how long does the person who did request 1 take? It's going to take this long, right? It's going to take the same amount of time. But request 2 came in right after that, and they're going to have to wait for most of 1 to finish, and then 2, which is that long. And request 3 was actually a really quick thing. It didn't take a lot of time on the server, but because it's backed up behind these others, it actually seems to the user like it's taking a long, long time. Why is that? If we zoom in, that's what's happening on the back end. Is we've got our web framework like Flask, Django, Fast API, ASP.NET, whatever. And then in there, we're writing a little bit of code to talk to a database. And then we have some logic like, I got the user back. If the user is not null or none, let's go do this thing, call another database query, and so on. Then we're just sitting here waiting on this database thing. Also, we might call an API here. We're also waiting on the API, right? So what actually happens a lot on APIs and websites is they're talking to external systems, file systems, databases, web APIs, like maybe I'm calling the Stripe API as part of a checkout process, whatever. All of those times, really nothing's happening. You're not trying to leverage a bunch of cores. You're just trying to, you just got to wait for a response to come back. But you could theoretically, in a better programming model, take those times where you're just waiting on the database and go do other stuff. Right. So if we change this around, if we didn't have to wait, our request could come in like this. Request 1 would still take the same amount of time, request 2. But because request 1 and 2 are probably in this waiting state, if we're allowed to do work while we're waiting, then actually response 3 could come back straight away. And so this actually looks like it even improves performance, although it really is not like the green bars or the base performance. And why is that working? Because over here, we can do work while we're waiting. So while we're calling the database, we can do more work. While we're waiting on the API, we can do more work. All right. Now, on the web side, when we think about the scale out across your cores, we often have some kind of deployment that looks like this. We've got Nginx and MicroWSGI or gUnicorn or some coordinating worker process sort of logic backend. And then what they do is spin up a bunch of different little machines. A request comes in and it just figures out which one it goes to here. So those processes can sort of do the job of scaling out across the cores. So when you're talking in the web scenario, the most important thing is to be back here and think about how can I do more work while we're waiting? Because that makes each one of these blocks on the right here, makes them able to do a ton more work, handle way more requests at a time without really adding any computational complexity. So in Python, we have different ways to do asynchronous programming. There's one aspect or one category of do more at once, and that's async IO and threads. Normally threads might be on the right as well. That's sort of the do stuff while you're waiting. Whereas we have multiprocessing, and you can use Python and C and other things that aren't constrained by Python's threading limitations to do sort of scale out on a single processor. And we also have these other cool libraries like Trio and Async. There's a bunch of stuff that you can play with. And the reason threads don't live in both categories, I suppose, is the GIL. Now, the GIL, or the global interpreter lock, is this constraint on Python, and it feels like it's a threading constraint that Python put in place, but that's not what it is. It's actually a memory management feature that has threading implications. So when you allocate objects or assign variables in Python, there's no memory management. There's no alloc and free and all that kind of business. It just does the tracking automatically, and it does that through reference counting. But anytime something is incremented or decremented, you want to make sure that's thread safe. So Python doesn't lock every assignment. That would be super slow, like a critical section type of thread lock. Instead, it just allows one instruction to run at a time, the global interpreter lock, so the memory doesn't have to have threading. But that means that basically the threading story for the CPU version isn't that great in Python. Here's a cool article from RealPython, realpython.com/python-gil, if you care. All right. So typically when we do concurrent programming, we think about the sort of fork and join model. Okay, so a request is going to come in, and then I'm going to kick off some other threads that are going to do some background work as part of that. And then we're going to wait till they're all done. And these other pieces kind of have to wait and then pick up the answers and keep going. The async and await model in Python, and to a large degree the other languages as well, doesn't really use that. It uses something very different. It's more IO driven, more event driven. And so instead, there's just one thread. There's actually no threading in this story. But what it does is says, let's imagine that we've got different tasks, like task 1, but it can actually be broken up into little segments. So maybe task 1 is register a new user. So first part of task 1 is query the database to see if that user with the email address already exists. If yes, then tell them you can't register again, whatever. Okay, that passed. So the next thing to do is go to the database and, you know, pull out some information, or maybe insert the record in the database. And then third might be to send them an email that they're registered, right? That'd be a real easy way to consider breaking up, say, a user account creation type of task. And we might have other tasks doing other things in the system. And if you could break that up into these little slices and you just said, let's run them, if any of them happen to wait, if there's any kind of blocking waiting period, like between the first and second orange bit, that maybe is the database query time, right? We could do other work if we could squeeze it in there. It's a very different way of thinking about concurrency. So this is how async and await works in Python. So it's just this async event loop just runs across these little broken up pieces. So the question becomes, how do you break up the pieces? That sounds very problematic. So let's start with a quick little building block, and then we'll see how to actually do it. So I'm going to show you something that seems unrelated to threading, the Fibonacci numbers. So here's a really cool implementation. I don't know if you know the Fibonacci numbers, but they're take two numbers and add them together to get the next number. So 1 + 1 is 2, 1 and 2 is 3, 2 and 3 is 5. And I've got this really cool implementation here. Do I have it up? Let's run that. And all it does is just return a flat list. So you can ask for how many. You say, I want 3. It's like, nope, you're getting 8, whatever. But let's actually implement this. I wanted to kind of leave it here for you to see how it goes. So let's do this instead. Let's come down here and say, well, the way the algorithm works is there's a current and there's a next. And I'd like to type next, but that's a keyword in Python, so I'll type this. And we'll say that's equal to 0 and 1. And then we'll say while, let's do it this way. We'll say for nothing in a range from 0 to the limit. We're going to need somewhere to store all these numbers. So we'll create a little array list here, and we'll say, here's a cool little way to do sort of swaps in Python. So we can say this is going to be current plus next, and then actually let's do next, and then current plus next. So that's our swap those numbers and increment it. And we'll say nums.append current. At the end, we'll return nums. Okay. So let's go ahead and run this and see what we get. 112, yay, it seems to work. Let's go and ask for some more. Let's go and ask for 12. So there we go. They're the 12 numbers. So that's cool, but think about this. The Fibonacci numbers, they're actually an infinite sequence, right? There's nothing where I said, you take the two numbers and you add them up unless it's less than 1,000, then you stop. This is an infinite sequence. So we can fix that, right? Let's go over here and we'll make a copy and chill that out over there. Now, just maybe there's no limit. So that's cool. We'll just write it like this. We'll say, we don't need this range. We'll just say while true. What do you think about this? I think this is going to work out well. Probably not, right? What's going to happen? We're either going to run out of time or we're going to run out of memory. And I'm pretty sure we're going to run out of memory really quick. So we're just going to keep adding to this list and it'll grow forever. And then eventually after forever, we'll give it back. So that's going to be a problem. And yet Python has this way, this really interesting way to partition functions up into little sections. That starts to sound a lot like that, breaking up your work, your code into these segments. So instead of saying return, what we can do is we can use this, this keyword called yield. And the way yield work is you just say, here's one of the items. Say what I'm going to get back from my function is an iterable from typing. I get just some iterable collection. And instead of creating a list all at once, as I go through my data, I just say, here's one of the items. And the way I tell Python, here's one of the items, is I say yield and then the item. Now, if I run this, it is going to loop over them forever, but so I don't want us to kill the system. So we'll say if n is greater than 1,000, we can break. And here's what's interesting is we're actually pushing the decision of how much do we want of this infinite series over to the consumer of the infinite series. All right, but let's run it, just make sure it doesn't not work. So look at that. Awesome. Very awesome, by the way. But check this out. So this is the sort of key to understanding what's happening with async and await. Let's put a breakpoint here. And if I step into my code, it goes down here. Now, normally that would step into this function above and it would show it running, but that's not what happened. We got back a generator. And as I iterate over, if I step in now, it comes in here. Notice it's on line 14 right at the beginning. That's cool. And then when I hit yield, it's back into the body of the consumer of this thing, which is interesting. And I step in again. Now, look, it jumps back into the middle though. Let me do it a few times so it's got some data processed. I'll do one more and then we'll talk about it. Notice when it jumps back in, it goes 3 and 2. It doesn't restart the function. So these generators and the yield keyword are basically ways to break up your big function into little bits. So I'm going to run down to my first site of the yield keyword, and then I'm going to sort of execute that and give that back. You can do whatever you want. If you want to come back to me, then you can resume this next segment, the true this, and then again in the next little block. So yield and these generators are ways to break up what looks like a regular function into a bunch of little pieces of work, which is super interesting, right? This should take, if you actually computed it all the way, this should take infinity time. And yet when I run it, it's near instant. Okay, super cool, because we only executed a few bits of that work. All right, let's take that idea and apply it over here. I'll just run this one. Okay. So I just want to get this ready. So let's check this out. So here's a real simple program, and it's sort of this producer consumer model. I'm trying to keep it real simple before we get into something concrete. With the producer consumer model, we have some things that are generating data. Imagine like some API requests are coming in and stuff's getting put onto a queue, and then it later needs to be processed, but we want to do it asynchronously. So we're just dropping it into this data thing that's being shared. And these generate data. This one takes data out to be processed. All right. This one over here, it's sort of saying how much do you want to generate. It's very contrived. Puts the data into the queue, and then it simulates this being real work by saying it's going to take between 0.5 and 1.5 seconds. So we're just going to chill. But of course, that would be actual computation, waiting on a database, waiting on APIs, file system, computation, whatever. And then this one's going to just go to the list here and say, I'm going to see if there's something in the list. If there's nothing in the list, we're going to just wait a little bit. And this is like pulling the list, and then we're going to process it. All right, so if I run this, check this out. Here it is. You can see it's synchronous. So all the first generate data is running. It's going to go up to 10. Then the second generate data is going to run. And the important thing about this program we'd like to optimize is how long does it take from an item getting in until the item gets processed? Imagine these are like, send this person an email. And if you're really busy, you don't want it to take forever for them to get their email. Like how frustrating is you go to a website, reset my email, and like 5 minutes later, reset my password. 5 minutes later, you still don't have the email, but eventually it shows up, right? You don't want that. But notice it had to do all the work and then process it. So let's do this with Python's async and await. So here now, this starts out to be exactly the same. It's the same code. But what we're going to do is we're going to use some fun new data structures. So we're going to import async IO. And this, instead of being a straight list, is going to be a queue. And this is super interesting because the queue has ways, just like our yield keyword did, to break up our function, our processing, into a bunch of little tiny pieces, just like yield did. And you don't really have to think about it. All right, so in order for this to be passed through, I've got to update the type annotations below. So I said this was a list. It used to be true. Now I say it's a queue. Okay, so these are no longer errors. Now the next thing to do is to convert these functions into something that can be broken up into a bunch of little pieces that the event queue, or the async IO loop, can process rather. And the way we do that is we say async here, and we say async here. And now instead of doing data.append, what we're going to do is we're going to take this thing that we're putting in there, and we're going to say data.put. Same thing. Now PyCharm says there's a problem here. Let's just hold on for a second. Let's go fix this one as well. Now this is really cool. See this pop, and then this test and this sleep. That's super janky. Let's not do that. let's just do data.get. Now there's some errors, warnings in the app here. What's going on? So what we actually get, if we look at item, it's a coroutine. That's the same thing as our generator, basically. And the way in Python we say run this coroutine up until basically run this coroutine is we have to say await, and that's it. So in order to convert this into something like our Fibonacci, we say it's an async function, and then we have to await the little places that would be the broken up bits. So here's how this one works. It runs up to here, and then that's one fragment of work for async IO, and then here's some more. And then it runs to here, and then here's one. This await is like, how do I break up my function into these bits? Same thing here. We have to await the item to get it back. So now item is a tuple of, basically that tuple right there, instead of a coroutine. That's cool. We could try running it. Turns out to not go so well. Coroutine process data was never awaited. So basically, you can't just run these directly anymore. You have to hand them over to the async IO event loop and say async IO run these, and then you have to come up with a mechanism to wait on them. Okay, so let's go here, do like this. We'll say loop equals async IO dot new event loop, and let's create some tasks. Do a little inline list type thing. And so I need these all in parentheses, so hang tight. I need them all to have commas on the end. Okay, so what we do is we say loop.create task, like this. So now that starts all of these running, but they're just going to begin running, and then we're going to exit and not get the results. Right. So the next thing we need to do is we need to say loop.run until complete. This is the blocking part. Say, okay, the program needs to basically wait for all these things, and maybe there's subtasks that we don't know about, which we'll see to wait. So we'll say async IO.gather, and you have to give it a bunch of tasks. I should take a list, but we've got to explode the list back to just a bunch of arguments that then become back to a list inside that thing. So, all right, so now let's try to run it and see how that works. It looks like it's still not working. There's one other part where we're not doing quite what we need to do. So it looked the same before. It didn't seem like we got any change. And the final change is this is simulating the waiting on the database, the waiting on the web API call or whatever. Now, time.sleep just really does put Python to sleep. But a better way to simulate that kind of wait that allows other work to happen is we can use async IO. So I can say async IO.sleep. But this one, you need to tell Python, here's a place where you can break up the code as well. So here's a piece of work, is print this and go back to, break it up to another slice. Get the item, put it in here. That's another slice. Let's try it now. Check that out. Okay, right as items are being created, they're instantly being processed. Basically that, this down here, this item, this data async queue is automatically like coordinating the waiting, resuming. Here's a bit of work. So pretty awesome. Like, think back to this here. You might have wondered, like, Michael, what are you talking about? How do you break this stuff into these tasks? This is insane. You just use the async and await keywords. That's it. And it automatically figures out like what fragment of that function to run. And then of course, internally those things use async and await, they become smaller fragments and so on. Very, very cool. All right. So if we look at this, the anatomy of these async functions here is it has to have async async def to define the function. And we have to use await somewhere to execute the sub coroutines and so on. All right. So very nice improvements. All the work ran, and then we got to all the work was added, and then we got to process it. If we async this thing, it breaks up just like you would think. Performance is way better. You can use this thing called UV loop, which is an ultra fast implementation using libuv. That's super easy to use. If you write this one line in the middle, async io.set event loop policy, UV loop, you now have a much more high performance internal guts of async IO, which is very cool. Unfortunately, it's great on Mac, it's great on Linux, but it doesn't work on Windows. You can still just use the basic one, it's just not as good. All right, so that all might have seemed somewhat contrived, but let's go and build something that does real work, like some web scraping. So let's go over here and do this again. I told you this was contrived, but just so we could kind of focus. This one is not contrived. This is a real thing doing real stuff. Suppose you want to do web scraping. Suppose you want to call multiple APIs at the same time. Like, I need to get the geolocation of this person, and I need to check, maybe I want to call Stripe as well. And then I need to pass something off to some microservice, and I need the order is independent of those things, but I just need them all to happen. That kind of stuff would super apply here, as well as I want to web scrape 1,000 things and I want that to be faster. So let's just run this boring old version here. So what it's doing is it's going to talkpython.fm, my podcast website, and it's pulling down the titles for episode 346, 347, 348, and so on. And the only information it starts with is there's episodes with those numbers, and then it uses the website. It literally downloads the entire page. So if we go over here to Talk Python, make it a little bit smaller, it like literally downloads this whole page here, and then it uses web scraping to figure out that that's the H1, and then it prints it out. Okay, so that's what's happening at each step here. We've got this main, and it just goes for 330 to 350, go get the HTML, and then there's this get title, which uses beautiful soup. It says parse the HTML, select the first H1, and then return the inner text of that H1. And the way it gets the HTML, so sweet how simple this is with the request. We just go, here's the URL, episode number, request get, and then make sure that worked and give back the HTML. That's great, but do you think that web server might be able to do more work? How much time are we actually spending computing our code versus waiting on the internet and waiting on the web server, which is in Virginia, all the way across the United States? Could we do better with async? You bet we could. So let's go over here and rewrite this with async IO. So we're going to write import async IO. Now, requests is one of the most popular packages out there. I think it gets something like 7 million downloads a week or something, but it's not well suited for this. So what we're going to do instead is use this thing called HTTPX, which I've specified here in my requirements. So we're going to use HTTPX because HTTPX has a way to write async code. All right, so let's see. Let's just make this function. This is the one that has all the waiting, right? That, in fact, line 11 is where all the waiting is. If we could somehow allow other stuff to happen while line 11 is running, we could unlock some pretty awesome magic. So let's say we're not going to do this. Instead, we're going to use what may be a bizarre language construct to you. Python has this thing called a with block, which sort of creates some object, does some work, and then closes it back up. So you might have like db create session, add session, and then down here you might do session thing one, do a bunch of things, and then it commits it at the end of that with block, right? That's been around for a long time. But this is where it gets interesting. You can have asynchronous blocks that basically anytime you're doing network database stuff, it allows that sort of management of that network stuff to be asynchronous. So we'll use httpx async client like so, and we'll just call this sucker client. And check this out. We go over here, and we're not going to do this request. We'll say client.get URL, and then client raise for status. This is all good. Except, what's the problem? It says coroutine doesn't have raise for status. So we got to await to turn that into a HTTP response. Okay. So that's great. This says basically run up to here until you open a network socket, and then run from there to here until you begin a network request and allow all the other processing to run, to do other things while you're waiting on the internet. and then do this final tiny bit of just make sure the status code is good and return the text that you parsed. So really great way to break up that work. And this one has no waiting. It's just given a text, a string, do processing on it. So it doesn't need to be asynchronous. But notice here, this thing now somehow needs to be turned into an async version because it says you expected a string and we got a coroutine. So we need to write a wait here. Cool. I'm just going to keep following along. Async IO. That's pretty cool. And we can just go down here, and there's a simpler version when this is a function instead of a list of tasks. I can just say async IO.run. I believe this will work here like so. And it'll work. Let's just make sure that it runs. Oh, wait, we're still running the synchronous one. That's not going to be super impressive. Let's run this one. Okay. Yeah, I forgot to tell you. I meant to have this error show up because HTTPX, a lot of people, when they use it, it runs into this error. It says, oh, it crashed, or it's not returning the right result. There's a redirect from the short URL. It actually said what it was. From this URL over to this great long one. Too bad. So in this request doesn't make you do this, but you have to say follow redirects is true. All right. But look, it's working. Wait, it's working just like the other one. What's going on? I guess it's cool. Maybe it could do more stuff. I don't know. I thought async was supposed to be cool, but doing real work, maybe it doesn't add anything. Well, it turns out you got to think a little bit more broadly about what's happening here. So when we do this bit right here, how many requests are running at the same time? Well, let's see. A request comes in. It says, okay, begin the request to tell the server to get, say, episode 330's webpage. Wait. Figure out the title. Now tell the server to get episode 331's webpage. Wait. Now get the title. That's exactly the same as blocking. There's like zero benefit. Not zero. There's nearly zero benefit to that. So let's make a better version here. All right. And the better version says, well, if you're going to somehow take advantage of this asynchronous stuff, you need to start all the requests and then process them. So we actually need to do this in like 2 steps here. So let's say requests, not the library, but the thing, is going to be this little list comprehension. So we can take this and say for each number, I want to go get its HTML. And we're going to do it like this. Okay, that's great. Now we need to start them. We need to create this task. So remember the way we did that was we can say we had a loop. I think we can just do async IO dot create task as well. Okay, that's good. And we're going to start them. And then we could just loop over the tasks for our requests. We can await this one to be done, and it'll block on the first one, but they're all running in parallel. Maybe the first one's done, and then the 5th one, and then the 10th one, and then the 2nd one. It doesn't really matter. We'll actually process them 1, 2, 3 in order, but they're still going to all be executing at the same time. There's one little weird glitch here, though. Notice we no longer have access to this number that we needed to pass along. This was episode number, like 332. So how do we get that back? So what we're going to store in this list of requests, let's call them tasks, tasks now, I guess. Requests, I don't know. Is we're going to put a tuple over here. So we're going to say, I would like to store the number and then the tasks. So we can then unpack them with n comma task, and we'll just await task. Okay, so you got to do a little bit of weird juggling to keep that data going. Did we make any improvement? Did it get any better? Let's see. All started, all done. Okay, just let's run it. I'll run it again. All the work's going, all the requests done. They're all started, they're all done. Compare that to this other one, which was do 1, then do 2, then do 3, then do 4, then do 5. Super cool, right? So very neat. And simple way to do like legitimate stuff, right? That sort of latency, I'm not sure if you see it over Zoom, but it sort of didn't instantly shoot out the titles. after they were all done. That little bit of delay is both waiting on the internet, maybe for like the last one to come through possibly, as well as there's actually a decent amount of computation to parse the HTML, to do the web scraping on the string and all that. So that part's not async. So pretty cool. We're able to break that up, and just once again, it's all about how do I break up my functions for two reasons. One, so it's a bunch of small pieces of work I can run in the async event loop. And then two, how do I do stuff while I'm waiting? In this case, what we're doing while we're waiting is processing the other pages, right? We kick them all off. As soon as the first one's done, we start processing this, and the other work can be coming in and so on, okay? So that's all about either something manual like create task or something really sweet like await. Okay, and then down here, we just say, all right, I'm gonna run up until here, open a network socket. I'm gonna run up to here to open this request, do other work while it's being processed, and then carry on. So super, super neat. Let's see what I got to say about this. So here's the sort of summary of this. The essence of this function is we got our async with block, and then we're awaiting the asynchronous web call here as well, using HTTPX because that's one that supports it. There are a bunch of libraries like HTTPX that you can use. You have awesome ones from MongoDB. You've got Postgres, you've got Redis. My favorite MongoDB one right now is Beanie. There. So Beanie is super cool. Beanie takes Pydantic, which is a fantastic data exchange API type of modeling layer, and MongoDB's asynchronous MongoDB library motor, and puts them together in a super cool way where you do something like create a nested document and just do product.find1 where product price is less than 10, and you await the database call again, just like you'd want to. In fact, when you're over on the website here, all of these things, if you pull up these different pages and stuff, they're super zippy. They're all using Beanie on the back end, by the way. So that's fun. All right, I was going to highlight a few more, but I think for the sake of time, probably say thank you. If you want to check out more about async stuff, I actually have a course over at talkpython.fm/async, so you can check that out. And with that, I would like to open it up to questions and thoughts. See some stuff in the queue. Yeah, go ahead.
Awesome. Thank you very much, Michael. Very cool. I think a few people like myself were waiting to see sync v async and how fast it would be in that live coding demonstration. I saw a few comments pop up and everyone was going, "Ooh, show us the difference, show us the difference."
Yeah.
Cool. Very cool. We do have a bit of time for questions.
Actually, let me round it out with one quick comment, since I think it'll drive home this point a lot. I had somebody reach out to me a while ago and say they were doing exactly this web scraping, not just to get the title. Like I don't know what they were doing. They were like pulling products or trying to check like multiple airlines, something like that, right? And they were doing this web scraping in the synchronous way, and it was going super slow. And they said, "Is there a way to make it faster?" So you should consider something like this. And they said, "I now have a new problem. I get so much data back from the internet. I ran out of memory and my server crashed." Because it was just like they sent too many. They didn't like limit it, like go get 100,000 web pages now, and all at once, and it did. So anyway, I thought that was pretty interesting. Yeah, let's do the questions.
Very good. Yes. So some of you have already popped in a few Q&As, but feel free to keep adding them. Use the button below, stick them in there. Let me just sort through a few. Got one here that says, with async and await, do requests return in the same order? So this is in reference, I think, to your scraping of your own site. Will episode 340 ever come before 339, as an example?
It's a good question. And the answer is yes, maybe. So like this, this scenario here where you start one, wait for it to start the next, it's always in order because there's only ever one in flight at a time. In this one, they're coming back in whatever order you want, okay? So, or not you want, that they happen to come back in, right? The internet has random latency that you don't know about. The website might process them in different orders because one of the worker processes was busy, or who knows, right? So these will come back. They will actually complete in different orders than you expected. But our program doesn't worry about that because we address them. We then go on to work with them in order, right? This list will always be a task for 30, then 31, then 32. They might finish behind the scenes where we don't know about it in different orders, but then we go, let's do 30, let's do 31, let's do 32. And sometimes the task will be finished by the time we get here. So await instantly returns the value. And other times this line 51 will block for a moment and then return, right? So let's say 33 finished before 32. So we get to 32. And this is going to block until 32 done. The next time through the loop, it's going to just give you the answer back because 33 is already done. So it really depends on how do you process it. There is a way. Is it on the loop? Maybe it's on the tasks. I don't remember exactly. There's a way somewhere to say, I want to wait, but give them back to me as soon as one of them is done. I think maybe it's the new event loop dot, where is it? I don't know. I shouldn't be fumbling around. There's ways to say run all of these and then wait for them to finish like we did here. But you can say basically give them back to me as they finish, or wait for just any of them to finish and give me the one that's finished. So you might do that if your goal was to process them literally as fast as possible. Like soon as 333 is done, I want that so I can start going on it. And then the next one might be 350, and then the next might be 330. You might care about that, but a lot of times I find you kind of want to just fan them all out and go. So there's the answer to that.
Very good. From Moss here, says he saw the note about DDoS. Do you have a way to avoid jamming up the web server while still using async?
The DDoS here, the DDoS here is sort of for be friendly to. Oh, this is the wrong app. Be friendly to me, right? If you put this, if you do enough of these, you'll start to hurt the server, right? Or any server, right? The more requests you send to it, up to the limit of your computer, it might not be great, right? So how do you do it? Imagine here, instead of having 20 things that we want to do concurrently, we might want to have 2,000. So you could do import iter tools, and then you could say parts, something like this, parts equals iter tools dot, is it chunk? What is it? Oh, there's a way. Chunk slice. Maybe it's not iter tools. Maybe it's in more iter tools. Anyway, there's basically what I would do is break this up into fragments. So give me 10 requests. Start those 10. Give me 10 URLs basically. Start the request for those 10 URLs. Wait for them to finish. Give me the next 10. Start the next 10 processing. Wait for them. So if you've got a huge list, break them into fragment sections that you run concurrently, right? You could do testing well, if I run more than 20 at a time, even not caring about them, it just makes it even slower for me because it starts to overwhelm the server. So break it into chunks of 15, whatever, something like that.
Yep. Very good. Here's an easy one. Todsby, what version of Python are you using in this demo?
We are using, does it say? No, it doesn't say. Sorry, we're using Python 3.10. But it works the same 3.7 onward. No, maybe 3.8. There is, there used to be a way, let's see, I can show you here. It used to be, you would say get event loop here. I don't run the right one.
I imagine a few people are on their stations at home following along. And
Yeah, awesome.
curious to know.
So you can see I ran it with get event loop and it's still running, but it gives you this warning, deprecation warning. There's no current event loop, blah, blah. This used to be the only way, and now they've made it more explicit where you have to create a new one or get the current one. So there are very minor coding differences from, I think, 3.6 to 3.7, but 3.8 onward, this should be all the same.
We may just wrap this up with one more question, just because
Okay.
of time, everybody. Another little one here. Are await fragments always one line of code?
No. It depends on what you mean by that. Let's see.
Yeah.
So when I talk about, I guess when I talk about this stuff, I like to think about it like, almost there, hang tight. That's not very efficient to get there. I like to think it about in these terms here, where you're like those colored fragments. So if you're talking about these pieces, they can be arbitrarily long or small fragments of code. So for example, in this one, the first fragment is to print that and then do that and then open the network socket. That's this first colored block. And then other stuff happens in the middle. And then the next block is one line, start the network requests. And then the next block would be these two lines, check the status and return the text. So very much like my picture, it's actually three fragments here. Although in reality, the first one would be very tiny, the middle one would be huge, the last one would be even more tiny, right? Because the first one's just open a socket, the last one's just check a number and return a string, and this one is wait on the internet and download. You know what I mean? Mm-hmm. So in that sense, if you think of it as those blocks, then it can be just however many lines you write between await statements, but there's not a way to like use the await keyword on more than one line in a sense. So, but when you think of the fragments that are executing, you want to think about like what is happening between an await statement and then either the rest of the function or, that's basically the side. You can write as many lines of code as you want here, right? You could print one, right? It's all those pieces. It's the last fragment.
Very good. All right. Interest of time, we will stop it there. However, there will be ways to talk to Michael. Thank you all for your questions. There are ways to reach out to Michael. We're adding some ways to connect with Michael in the chat. But Michael, what's the best way for your audience to connect with you? Do you have a preferred channel?
Probably the best. There's two ways. You can reach me at mkennedy, MKENNEDY on Twitter, or you can just email me, michael@talkpython.fm. Those are probably the two best ways.
Perfect. There you go. And any final thoughts or encouragement that you'd like to give everyone before we officially end the session?
I've got some. You hear people say two things often about this type of programming. Thing one is it won't make anything faster. I tried it. We did some benchmarks. Benchmarks were flawed. And it didn't go any faster. You really got to think about, is there something you're waiting on that then you can scale to do other stuff while you're waiting? And, like my very last example of, oh, look, we added async to the web scraper and it didn't go any faster. Well, you didn't actually start more than one request at a time. That's why it didn't go faster. It probably actually went slower. So you've got to think slightly differently, but it's also ties into the second thing I want to add is a lot of people say it's super complicated. This threading stuff is so complicated. Like people should never write threaded code. It's beyond humans. Don't do it. I don't think anything I wrote was particularly scary or hard or tricky. There is threaded code that is very complex, but the async and await model actually doesn't even start other threads. There's no thread locking. You didn't see me use like locks or rlock or any of those things that you would use for thread safety because there's only one thread and it would be ineffectual, basically. So there's a lot of cool things you can do that don't require you diving deep into like what people might consider scary territory with like events and signaling and C++.
Very good.
That's it.
All right. Thank you, Michael. Very, very very much a pleasure to have you here. That was fascinating. I was glued to the screen the whole time. So if I missed you in chat, please be aware I was learning too.
Awesome. Thanks, Elliot. Thank you, everyone, for coming.
Pleasure. That is the official end of this session. So thank you all for joining. A very quick reminder that we have a swag giveaway going. So don't forget to use the hashtag DGS2022 in your social posts to increase your chance to win. Also, if you'd like to be a speaker of your own event in the future and share some experience with fellow devs, please check out our Codementor Events homepage. We have events every week from all walks of life. Links will be in the chat. The next event will be Using GitHub to Power Up Your Static Sites by Annie Liu, happening shortly at 11:30 a.m. Pacific time. So I hope to see you there. We'll leave the webinar open for maybe about 2 minutes with the information showing. And if anyone wants to network very quickly, but then we'll be closing it for setup. So thank you all very much for attending.